a little late, but hey, at least this is stuff that I think you guys are going to be pretty familiar with, so we'll be able to move relatively quickly through this material. So, we're focused on electronics, right? This first chapter is on the fundamentals, okay? So, voltage, current, resistance, and all that is the first lecture. Two quantities, as you guys know, will be of special importance in analyzing and designing electronic systems: voltage and current. Okay, those are the two variables that we use to describe electricity in circuits. Of course, there are also other quantities that we'll discuss, charge and whatnot, but those tend to be less useful when you think of the system, the circuit as a whole. Okay, so the relationship between voltage and current defines a third important quantity called resistance, or more generally, impedance. Okay? So that's our sort of broad overview of what we're doing here. Momentarily, we will define each of these, but we start with the fundamental quantity in electronics, electric charge, which is a property of matter that describes the attractive or repulsive force acting on the matter in an electric field. At the microscopic level, charge is quantized, which means that it has discrete amounts, into charges of subatomic particles such as protons and electrons, which have opposite charges, E and minus E, or negative E, where E is the elementary charge. Okay? So that's stuff that you probably talked quite a bit about in physics. They were really interested in getting you to understand electricity, charge at the microscopic level. In this class, we will be less concerned with the microscopic level and more concerned with macroscopic phenomena that have to do with the charge moving around and building up places. So charge has derived SI unit coulomb with symbol C. It is considered to be a conserved quantity. Voltage is the difference in electrical potential energy of a unit of charge moved between two locations in an electric field. Okay? So it's a potential energy. So think about that. So the voltage is the difference in potential energy. So when you have a voltage, you have the ability to do work, right? You have some sort of potential energy that is ready to be delivered to some system, which is why we often will think of our sources in electronics as being voltage sources. They're not always voltage sources, but we'll talk more about sources later. Okay, so voltage is typically given the variable V, so it's lowercase v. I will be, when I draw this, I won't use a huge fat marker. I will instead, I will use that for V because the difference between this and this on the board is really hard to see. So for capital V, I'll do this. For lowercase v, I'll do that, just so that you can kind of tell the difference. Okay, it has derived SI unit volt with symbol V, big V. Oh man, I bled all over my laptop. The first thing I thought, it's terrible. The first thing I thought when I went down was, okay, first of all, like, I'm numb most of my body, so I have no idea what happened, but like, where's my laptop? I hope it's okay. Turned out it's fine. This is good. All right, so voltage is always defined by referring to two locations. Okay, this is important. Sometimes we'll talk about the voltage at a certain point, but we really need to always remember that it is in fact always reference to two locations. Sometimes one of these locations is implicitly ground. Okay, ground is an arbitrarily defined reference or datum voltage considered to have zero electrical potential energy. So remember in mechanics and physics, you had gravitational potential energy, and you had to describe, or you had to define a datum a height, say, in the gravitational potential field that was defined to be zero potential energy. So maybe that was like literally like the earth ground, or maybe the floor, that was going to be zero potential energy. You had to choose a point because that was the reference for whatever potential energies you used in that problem. Okay, so it's the same with voltage. We're going to have a ground for voltage. That's what we're saying. So there's no like universal ground for voltage. It's just something that's defined in the problem that you're working. So you will say this point in the circuit is ground. And that's fine. You can choose any point you want, and that's going to be ground for the rest of the circuit for that problem. Okay? You just got to stick with it. You can't switch grounds. If you have multiple grounds that aren't actually the same in a problem or in an actual circuit, it causes no end to headaches. So they call them ground loops, and it's a huge problem. Sometimes you think they're at the same ground and they're not. Okay, so sometimes we define one of these locations to be ground, such that we can talk about the voltage at this or at that location by implicit reference to ground. It's good form to describe the voltage as being between two locations or across an element. Okay, that's a little bit more descriptive. Otherwise, you're requiring the reader or the person listening to you to know what you're talking about in terms of the ground. Know what your reference is. So, current. Current is a flow of charge. It's a pretty simple definition. So you've got charge, this fundamental quantity that's conserved, and it flows around. If you build it up in a place, it has potential energy, voltage. Okay. If you flow it around, we call that current. Current's typically denoted lowercase I and derived SI unit ampere with symbol A. Due to this notation using I for current, we will avoid using, we will not use this notation in this class. Okay, we will not do that. It's not equals. The imaginary number in this class will use J for this reason. In electronics, this is standard. So electrical engineers, they always use J for the imaginary number. And we'll adopt that convention in this class. It's a good convention because otherwise it gets really confusing when we get to impedances, complex numbers will come in a minute, and then, or not a minute, but next week, maybe this week. I don't know. Lecture 3, I think. So we're going to avoid using I for imaginary numbers. Okay, it has derived SI unit ampere. Okay. We typically generate voltage by doing work on charges. Okay, so this is a little bit of terminology. Conversely, we get current by placing voltage across matter through which current can flow. This implies that voltage causes current, right? This is the sort of way that we typically think about it. The voltage, you put it across something and it flows current through that. Causality here is actually quite complex, but I will posit the following proposition. We typically observe current when applying voltage. So from a phenomenological point of view, it is natural to consider voltage causal of current. There are really interesting discussions about this in the sort of philosophy of science literature. It's some fun reading, and I think I have a reference there in the footnote. Do I? I think I do. I didn't give you one, but there's a whole body of literature on it. And if you're interested, I could probably point you to some. Okay. So we typically think of it as we apply voltage and we get current. Okay. Circuits. Electric circuits are dynamic electrical systems in which charge accumulates in and flows through elements, okay? So, I mean, you guys have already seen circuits, so that's, I should get a helmet like that. That would help. Yeah, so it accumulates in parts of this circuit and it flows through the elements. Circuit elements are connected via metallic conductors called wires, which ideally have the same voltage everywhere. Same voltage, of course, relative to ground. So we say that a wire is typically good enough to approximate a perfect conductor, okay? So in reality, wires have a little bit of resistance to them, which we haven't actually talked about resistance yet, but they aren't perfect conductors. They don't have the same voltage everywhere on them. If you get a very long wire, you start to notice effects from that, but typically they're negligible for short wires. So we'll often ignore it. But for power transmission over long distances, it starts to become an issue, so you have to take it into account. Circuit topology. A circuit has a few basic topological features. A circuit node is a continuous region of a circuit that has the same voltage everywhere. A node is an idealized concept that is approximate in most instantiations. So a node is like everything along a wire is going to be a node, right? Because, so say, we haven't talked about resistors yet, but I know you guys all know about them, so I don't have to pretend like you don't. If you have two resistors connected by some wires, all of this has the same voltage. All of this stuff here has the same voltage, right? So say this is a wire that's connecting it, and then maybe these are leads coming off of the resistor, each resistor. We would say, oh, okay, all of this stuff is essentially perfect conductor, close enough to a perfect conductor. We can say that all of this is at the same electrical potential, all of it's the same voltage, so this is a node. This is another node down here. Everything's at the same potential. Yeah?
Is there a difference between leads and wires?
So, only from the perspective of looking at discrete components. So if you looked at a resistor, like a real resistor, it would look like, not bad, that. And it would have some stripes on it, right? And the metallic bits sticking out of the end are called leads. But they're effectively wires. We would typically have a wire that's coated. Wires would typically be coated, whereas a resistor or other discrete elements like this have bare metallic, cylindrical, flexible. Sorry?
Wire link?
Wire link, yeah. It's essentially wire, but when it sticks out of a discrete component, we call it a lead. Yeah, it's a sort of terminological thing. They effectively do the same thing. They conduct electricity through them relatively well. Good question. A circuit element is a region of a circuit considered to have properties distinct from the surrounding circuit. Examples of elements are resistors, capacitors, inductors, and sources. So in electronics, we've got all these discrete components that have been more or less codified and normalized over time. So capacitors are like this, resistors are like this, inductors are like that. They have, every manufacturer does things a little bit differently, but for the most part they have a lot of similarities, and they're relatively uniform. And we can expect certain things from these, certain behaviors from them. Okay. A circuit element has terminals through which it connects to a circuit. So another term for these, so it kind of sucks because there's a lot of terminology, and I don't want to confuse you, but I also want to give you all of the terminology that's used. So terminals is another sort of name for something like this, so also called terminals. Terminals is a little bit broader of a category, though. It doesn't have to look like a lead. A lead can be a terminal, but not all terminals are leads. Okay. It could be like a plug. Yep. You could have a just bare copper faces that could be soldered to. There are a lot of different types of terminals, and that's why we sort of use this terminal terminology. Terminology, because it's sort of general. And so however you connect to it, we're not going to say, oh, it has to look like this. It's however it connects to the circuit, whatever the connection it is. We call it, to call those the terminals. Circuit elements in parallel are those that have two terminals, each of which is shared by another element's two terminals. Okay, so this is a huge gotcha. A lot of people have trouble determining if two elements are in parallel or in series, and I know if I do this, you guys will get the right answer. It's series. And then if I do what I drew before, this is in parallel. So that's great. But then sometimes you'll have things that are in a bigger circuit, and it won't be as obvious, and they won't be drawn. Like, for instance, what are these resistors? Parallel. I know, but there's a lot of times people get tripped up. So that's good. I'm glad you guys recognize that. So the key, if you go back to the definition of parallel, then they're shared terminals. So shared terminals. This one only has one in common. So a circuit element in series. Circuit elements in series are those that have two terminals, only one of which is shared between them. And this one cannot be shared with any other element. So if you had another element coming off here, then these would no longer be in series. Okay, so that. Element types. The following are common types of circuit elements. Energy storage elements store energy in electric or magnetic fields. Okay? Capacitors store energy in electric fields, and inductors store energy in magnetic fields. We'll talk more about those elements later on. Energy dissipative elements dissipate energy from a circuit, typically as heat, such as a resistor. So a resistor is the quintessential energy dissipative element. You need resistors a lot. You're not always trying to just dissipate energy with them. You're trying to maybe change the voltage level, for instance. There are a lot of reasons to use resistors. But what is often a negative side effect of resistive elements is that they dissipate energy. Okay? And it's negative from two perspectives. The first is you lose energy, which sucks, right? But second, you generate heat, okay? And heat, actually, I would say one of the hottest maybe job opportunities right now for MEs is thermal management for server farms. So like Google, Amazon, these companies, they have these huge server farms and they've got little circuits running all the time. The more cycles, the better, faster things are going, but generates heat. And if it gets too hot, then it can damage the components. So they have to reduce the throughput of the processing power. So cooling it down becomes a huge, important problem. Okay, so thermal management, due to this dissipative effect, is a huge deal these days. And it's a pretty cool thing. MEs get involved in that quite a bit. So Intel is a company we've had quite a few of our students work for them after graduating, and they've had our senior design projects from there. We have somebody on our engineering advisory board from Intel, and they're always working on like ways to get heat off of processors and out. So yeah, it's a pretty cool area. All right, energy source elements provide external energy to the circuit. For example, batteries. So the first circuits you guys probably built, you took like 9-volt batteries and you had like a light bulb and you connected, right? That was probably, or you put steel wool and burned it. That's fun too. That was what I would do. I don't know why. My mom like gave me this like lantern battery and a bunch of stuff, including steel wool. I was like, this is dangerous, but okay. This is like a little kid playing with things, making like booby trapping the rug at the bottom of the stairs so that if somebody stepped on it, like it would put 2 pieces of foil together and a buzzer would go off. Yeah. 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 It makes sense now. Okay, so energy transducing elements convert electronic energy to another form. For example, motors convert electric energy to mechanical energy. So this is actually where we're headed, right? We're headed towards this energy transducing elements type of element. But we have to understand mostly the electronic stuff first before we can get there. So that's what we're going to build to. Power is the time rate of change of energy. So that's been true ever since you've heard of power. So no surprises there. Let's define electric power. The instantaneous electric power P into a circuit element is defined as the product of the voltage across and the current through that element at a given time t. So VI, the product of the voltage and the current, is the power into a circuit element. Okay. So if it's power into a circuit element, we're going to talk about sign conventions later, but a negative power would mean that it's leaving the element, right? Power is leaving the element. Power typically goes into heat, which is usually what happens, sadly. Mechanical work, motors, radiated energy, lamps, transmitters, stored energy, batteries, capacitors, etc. So especially if you're doing any sort of processing, like computer processing, the product that you see come out of that is essentially just heat. I mean, it's in terms of power. You get information that gets processed too, but that's not, I guess, direct energy. So it is related to entropy, though, so that's kind of an interesting one. So terminological note, and maybe I put this in there because I think that it's kind of funny, and it gives you an idea of what reading this Art of Electronics textbook is like, maybe to motivate you to read the actual prose from the text. So they say, don't call current amperage. That's strictly Bush League. I always liked it when they said that. The same caution will apply to the term ohmage for resistance. You don't like to use those terms. Amperage is something that you hear quite a bit, and if you use it, I'm like, that's not a big deal. But we prefer the word current. Amperage is like, I don't really care, but like somebody, if you say it out in the workplace, people might think you're like, oh, okay. I see. Okay. They might judge you for it. So just so you know. Kirchhoff's laws. So Gustav Kirchhoff. I had to put his name in full name because it's so cool. Gustav Kirchhoff formulated 2 laws fundamental to circuit analysis. And this is probably like where you guys have spent a lot of your time in electronics, is dealing with his 2 laws. Okay, so Kirchhoff's current law, KCL, is how we often abbreviate it, depends on the fact that charge is a conserved quantity. Therefore, the charge flowing in a node is equal to the charge flowing out, which implies Kirchhoff's current law, which is the current in a node is equal to the current out. Okay? So current in equals current out. There can't be any lost charge. Okay? And the node is all at the same potential. We don't have any discrete elements in there, so we're talking about essentially nodes in your circuit, right? So current in is equal to current out. KCL implies that the sum of the current into a node must be 0. Assume, for instance, that K wires with currents IJ connect to form a node. So I'm using J here as an index, okay? So K wires, they each have their own current. They connect to form a node. Kirchhoff's current law states that the sum of those currents into the node is equal to 0. It can be discovered empirically that elements connected in parallel have the same voltage across them. This doesn't mean they share the same current, but it does imply Kirchhoff's voltage law, which is that the sum of the voltage drops around any closed loop is 0. I didn't define a loop yet, so I'll say a loop is a series of elements that begins and ends at the same node. So if you go around and you come back to the same node, you went on a loop. So it says the sum of the voltage drops around any closed loop is 0. So those are the 2 laws. We can also do this mathematically. So the voltage drop across elements that form a loop must be 0. Assume, for instance, that K elements with voltage drops Vj form a loop. KVL states that if you sum them up, you get 0. Sum up the voltages around a loop, you get 0. Okay, so KCL, KVL, no problem, right? These are what you guys have been using probably in your circuit analysis so far. Ohm's law is the other thing you guys have been using. Much of electronics is about the relationship between a voltage and a corresponding current. Applying a voltage to a material typically induces a current through it. The functional relationship between the voltage and current is of the utmost importance to the analysis and design of circuits. The simplest relationship, so we'll start with the simplest. Okay, the simplest relationship is known as Ohm's law, for which we will need the concept of resistance. So let a circuit element have voltage V and current I. The resistance R is defined as the voltage V divided by the current I. So we're now ready to define Ohm's law, which is surprising. We often call this Ohm's law, but it's technically Ohm's law is some materials, such as conductors in certain environments, exhibit approximately constant resistance or approximately constant V over I characteristics. So there are a whole lot of elements that don't follow this. In fact, most elements don't follow this that you're going to put into a circuit. But some do, and we call those things resistors. Okay, so it's pretty weak. However, it's still quite useful, as we'll see. With it, we can assume for certain elements and situations that the resistance of the element is a static property and that the voltage and current are proportional. We call such elements resistors. So that's our definition of a resistor. So that actually means that we have these discrete things you can buy called resistors, right? What they're saying is these things behave like Ohm's law, okay? Or at least approximately in some operating conditions. And in fact, even those things you buy that are called resistors don't act like resistors in this ideal sense all the time. When they get hot, sometimes they'll change resistance a little bit. If you run too much power through them, you can damage it, and then it really doesn't act like a resistor. So there are conditions under which even things we call resistors act like ideal resistors. And then there are other things that are not sold as resistors, things such as wires that have resistance to them. Okay? So resistance is a property of elements that goes beyond just these discrete things that we buy called resistors. It's important to keep that in mind. Combining resistance. This is something I think you guys have also seen. Resistors can be connected together in different topologies to form composite elements that exhibit equivalent resistances of their own. I've noticed when students panic on exams, they just start combining resistance. It's like, I don't know what it is. At some point, some teacher pounded how to combine resistances into your head in parallel and series, and that's like the default. That's what everybody goes back to, and they're freaking out on an exam. It's cool. I get it. You're having some anxiety about the exam. You just start combining resistors. It's not a bad idea. You could be right. It's just apparently the knee-jerk reaction. Okay. K resistors with resistances Rj connected in series have equivalent resistance, we'll call it Re, given by the expression Re is equal to the sum over all of the resistances in series. So just add them up. If you have a 50 ohm resistor and you have a 200 ohm resistor and they're in series, you now have a 250 ohm equivalent resistance between those two. K resistors with resistances Rj connected in parallel have equivalent resistance Re given by this expression, which is 1 over the sum of 1 over the resistances. Okay. So if it's just two resistors, R1 and R2, we have that Re is equal to 1 over R1 plus 1 over R2, which is equal to, doing a little bit of simplification, R1, R2 over R1 plus R2. When you combine more than that, don't skip this. So this is useful to remember, just off the top of your head. Combine two resistors. You do it all the time, so it's kind of nice to have that simplification in mind. But go back to this formula if you've got more than two together, because you don't just simply add just multiply this by R3 and then plus R3. That's not actually how this goes. You have to. There is a pattern that emerges, and if you want to memorize that pattern, it's fine. But recognize that it's not the naive pattern. It's a little bit more complicated than that. So this one's nice. This one's nice to remember, sort of committed to memory. There's not a lot of things that I recommend you memorize, but this is one of them I think is good to memorize. Yeah, you do R3, and then it's R1, R2, R2, R3, R1, R3, plus R1, R3, yeah, in the denominator. So it's like
A lot more.
you have to remember all the combinations, which is fine. I mean, but you could always go back to this formula. I recommend just going back to the formula and then deriving it. Yeah, it's just gets a little crazy. So understanding a circuit. Here's an example. Answer the questions below about the circuit shown. Okay. Voltage across and current through a circuit element X are denoted Vx and Ix. Signs are defined on the diagram. So here's the diagram. So R1 and R2. So we haven't talked about sign convention yet. So I went ahead and just said, okay, a positive voltage across R1 is going to be from this side to that side, a drop from plus to minus this way, plus to minus that way. Okay? So I defined all the signs, and I said there's an R1 and R2. So this is a simple circuit, right? Just two resistors and a voltage source. Here's our ground. This is the symbol we use for ground. Okay? So we can use, there are other symbols too, and they mean slightly different things in different contexts, or it means you're just in a different country because different conventions. But this is the one we typically use. Okay. Okay. So what does it mean if we refer to the voltage at node A? So this is node A. I just defined node A to be that. So I don't have a ton of time, but we can at least talk about each of these. So voltage at point A. What do I mean when I say what's the voltage at point A?
The difference of potential between A and ground.
Exactly. The difference in potential between A and ground. So it's equivalent to the voltage across R2, right? Because the other side of R2 is connected to ground. It's also equivalent to the voltage across R1 and Vs, because that also gets us to ground. So it's the difference in potential between A and ground. Could be 5 volts or whatever it is. Great. What is the current IR2 through R2 at a given time t in terms of the power it is dissipating, PR2, and the voltage across it, VR2? Yeah, so this is a sort of pulling in a formula that we saw before, the definition of electrical power, right? So power at a given time is equal to the voltage at that time times the current at that time, right? I said, and if we're going to use specifically R2, so we would say PR2, VR2, IR2. A little cramped, but you can tell. This implies that if we want to know the current, IR2 equals PR2, PR2 divided by VR2. Which I gave you, well, I didn't give numbers, but yeah. Okay? Is that clear? Any questions on that? Cool. 3. If Vs, so the voltage source, is just a constant 5 volts, what we'll later learn to call a DC voltage source, and VR1 is 3 volts, what is VR2? Okay, so Vs is 5, VR1 is 3. So you guys are saying, oh, it's 2. What did you guys use implicitly when you said that? Kirchhoff's KVL, right? KVL told you that VR2 must be equal to 2 volts. Yeah? Good. Exactly. If you go around the loop, you should get 0 volts total. Great. 4. What is the equivalent resistance of the resistors R1 and R2 combined as in the circuit?
R1 plus R2.
Yeah, so the equivalent resistance, they're in series, right? They share one node and no other element connects there. Siri keeps thinking I'm talking to her, but I'm not. R1 plus R2. So they're in series, and we just have the sum. Okay? 5. If VR1 is 3 volts, the voltage across R1 is 3 volts, and R1 is 100 ohms, then what is the current through R1? Or R2, actually. What's the current through R2? So this is 2 steps we got to do here, right? So if we know the voltage and the resistance of R1, we can find the current through R1 using which law? Ohm's law gives us that the current through R1 is equal to what? Okay, and what I gave numbers for this too, right? So 3 over 100, right? And the units are going to be amps, right? Pardon?
Can you use like 30 milliamps?
30 milliamps, yeah, 30 milliamps, or 3 milliamps. No, 30 milliamps. You're right. 30 milliamps. 30 milliamps. So if we have the current through IR1, we want to know the current through IR2. Which law should we use?
It's the same current.
It's the same current, and we know that through KCL, right? Kirchhoff's current law tells us that all the current coming into this node must equal the current going out of this node. So this is true. Whenever you have any series elements, the current is the same, right? So KCL tells us that IR2 equals IR1 equals 30 milliamps. Awesome. I know it's kept you guys a couple extra minutes. Thank you for being patient. And yeah, I'll see you Friday. I want to see everybody's notes on Friday. Yeah. Most of you